Let's see. Let me know if you're here and having a great day. Let me know if you're here. Ah, fabulous. That is correct. Hello, hello. Tell me, please, wonderful people, can you see what's going on? Say anything you like in the chat. Anything wonderful, anything glorious, whatever's going on in the world. Need to just get some bits going. Okay. Lovely jubbly. I think we're all ready. Right, we've got hello from myself, just testing that things work out. Ah, it's not snowing, is it? I've just turned around, it's not snowing. You scared me? You made me think that it's snowing. Amazing. Hello, wonderful people of the internet. I hope we're well. I'm quite excited for today. The learning I had to do to oh, it's in Glasgow. Oh, fabulous. The learning I had to do to kind of get my head around what we're learning about today. It's so interesting. This is some of the coolest stuff. I'm just going to give a couple minutes for people to log in. Excuse me, get ready. Log in, get ready. But while you log in and get ready, I'm going to just load up. Oh, how exciting. Just load up what we're looking at today. Let me think with my brain. Let's just do this. Mate, fabulous. Alright, that works. And hopefully if I do this. Ah, fabulous. There we go. There you go. Can you see that? Hopefully that's working just fine. You should see space, the formation of stars. Let me know if you can see this. Hello. Hopefully you can see. Good evening. Hello. Yes. Okay. Fabulous. We've got shrimpanzee. Oh, excellente. All right. Cool. Just double checking that we've got the right things up. So, what I'm talking about today is just going to be exemplary, interesting stuff. What we're learning about today is actually exactly the same information that my year 11, so that's 15, 16-year-old students, need to know for their real GCSE exams, so the exams they do at the end of 15, 16 years old. And this is specifically the kind of knowledge that you learn only if you're specifically learning about physics, right? It's called triple science in England, and it's something very specific, and not everyone gets to learn this. This is something I made for my Aim High tutor group that we've been doing on Mondays, and they found it so interesting. I found it so interesting to build in the first place. They found it so interesting, so I decided to take it to an Aim High today. One thing that I want to let you know about is that it's currently 7 o'clock. It might take about an hour, a little bit longer than an hour, so we'll see how it goes. I'm going to try and get through, but there's so many cool interactive information. So, hi, I'm Josh, and I'm speaking to you from London. I am a secondary school science teacher. I'm the head of science at a secondary school in East Finchley, and I'm talking to you from Aim High, which I've been working with since lockdown 1. Aim High is a nature-first, curiosity-powered online school where our mission is to make world-class live learning accessible for everyone. Today's lesson is called When Will the Sun Explode? And we're going to be talking about that concept. But to be honest, such a question is such an easy answer, right? You can get an answer very quickly online, but we're mainly going to talk about how the sun came to be in the first place, our beautiful star known as the sun, but then what's going to happen next in its life cycle. Overall, you know, how far in are we in its life cycle? How long is it going to be until it, well, supernovas one way or another? What I'd love for you to do is to take some notes, ask any questions as we go. Make sure to feel totally free to comment or interact wherever you'd like. There's no such thing as a stupid question here. Don't always feel free that your question is going to be worked on. We are so used to loads of questions at a time, and we're going to really be excited to interact with as many as that come up. Also, if you're interested, you can also talk to each other. You can respond to each other's comments as well. So, can you check that your chat is working by typing in your favorite celestial body? Your favorite celestial body. So that's anything in space, which arguably is anything in the entirety of the whole universe. So yeah, just type something in, check that your chat is working. Anything in the universe, any celestial body that is your favorite thing. Sirius, amazing. Is that Sirius A or B, Suzanne Tumnus? We've actually got a little bit of information coming through. The Earth, fabulous, by GG Hall 35. Yes, the Earth with everything and everyone you've ever known and loved has been on it. Anyone else want to give something interesting from the entire cosmos that they find incredible? Oh, it can be anything, Leonardo. Anything really cool. Comets, says Shrimpanzee12. Black holes, says Katie Abir. Amazing. Claire Thomas says black holes as well. Amazing stuff. Mate, we're going to be talking all about this all today. Now, my first question for you all. Hello from Kelly and Thomas, age 10. Hello. Oh, the Crab Nebula. The Crab Nebula by Michael Farfan. Thank you. That is absolutely beautiful nebula and something we are going to be looking at later on. Betelgeuse. Amazing, Leonardo. Can you tell us what Betelgeuse is? Anyway, while Leonardo is answering that, I want you to look at this image here. This image is quite a cool image because ultimately it's saying that there's something about 8 minutes going on from the sun to the Earth. I wonder if anyone knows what that is. And when we're thinking of that, the star on the armpit of Orion. Lovely, lovely jubbly. Now, here is our sun, and it's 8 minutes, something's going on in 8 minutes. Once you're thinking about this, I also want you to think about what would the Earth be like without the sun? Well, if I click my fingers and the sun just disappeared, what would happen? Suddenly, without the sun, what would happen? So 2 questions there. One is, what's this 8 minutes got to do with anything? And the second thing is, if I were to click my fingers and say goodbye to the sun, what would happen? Brilliant, says Shrimpanzee12. Things would get a lot colder, right? Things would definitely start to get a lot colder and we'd start to freeze. Shrimpanzee, interesting follow-up questions. Do you think, is the heat from the sun the only place that the Earth gets its heat from? Interesting. There would be no Earth, says Cal Thomas 10. What do you mean? You know, if I click my fingers and the sun disappeared, the Earth would, the mass that is the Earth would still be there. A lot of darkness. I like that idea. But I mean, without the sun, would all the lights go off? Like the lights in my room, would they just disappear? Would it just turn off? Now, Leonardo Pess has got such a cool idea. Excuse me. We wouldn't know for 7 minutes. Actually, it's about 8 minutes we wouldn't know for. If the sun just clicked and disappeared, the amount of light that it's produced, it would not slowly, flipping heck, it would travel at the speed of light. At the speed of light, it would get from the sun to Earth and then just stop. That light would no longer come from the star to our sun to Earth, and we would see darkness. So it'd take about 8 minutes for us to clock it. Dark and cold. There'd be no water cycle. What do you mean by that? And why would that not happen? Any other ideas of what might happen? Maybe, any ideas about the orbit of the Earth? What could happen to the moon? What could happen to the other planets? What would happen to the plants? What would happen to the animals? Come on, we can go a bit further into this. Amazing work by Leonardo. There'd be no photosynthesis. Good, no photosynthesis, or at least for natural photosynthesis from the light from the sun would definitely stop. Obviously, again, you know, our lights would still be on, so we could do that, but no, there'd be a huge swathe of organisms, plant-like organisms, as well as algae and phytoplankton in the sea that would just no longer get any sunlight, no longer photosynthesize. But what would that mean? The Earth would move away in a straight line. Oh, I love that. Cool. So it would just fling off into orbit. Bye. Just go away. I mean, interestingly, what would it actually start to orbit? You know, the Earth is going to start orbiting something else if the sun disappears. There's something that also has a massive mass in our solar system that the Earth would actually not necessarily start to orbit like the sun, but it would definitely start to turn towards it. Gravitational pull. Yes, exactly. There'd be no gravitational pull from the sun. Really, really cool. Some of this stuff is just incredible. That's exactly great point. I wonder if that's actually a word. Gurjurgerhaska. There you go. Gurjurgerhaska. That's your name for now. Our sun, as you obviously can tell, is so hugely important. Without it, we wouldn't have the warmth in our bodies. Yes, there would still be a little bit of warmth from the Earth's core. However, the vast majority of our warmth would go. It would be immensely dark. And over time, it would just get darker and darker. Because yes, we've got the electricity that we've got around us. But, you know, over time, we're not going to have energy that is coming from the sun to give us that electricity that we currently hold. Came from ultimately the sun. All of the solar panels in the world ultimately are powered by the sun. Even wind energy, hydroelectric energy, all of these things are ultimately powered by the sun. And this is obviously incredible. And without the sun, well, we wouldn't be here in the first place. But let's have a look. What I wanted to look at is a bit of scale of the formation of these universe. Just a little look about scale. Whoopsie doodle. Right, just a little look about scale, because the thing is that it's quite difficult to really envision how big things actually are. So what we're going to do is we're going to watch a video together. It's a very short one, very short vid, one without really any music to it. I'm going to speed it up a bit, but I'm hoping to blow your teeny tiny brains. I'm lying, I know that all your brains are huge in every way, shape or form. But you may have seen this already, you may have not, that's absolutely fine if you have. But what I'm going to do is just post it to everyone so that you can have a look at yourself at your own rate. I've sped it up a bit just to make it move a little bit quicker. But I just want to show off just how big and how small things are. There are a number of emotions you might feel during this. I'd love to hear them as you're listening. Okay, so let's keep going. So here we have Mars and Venus and Earth. We've gone through a number of moons up to this point. You know, we're about as big as we think we should be at this point. Here's a cheeky bit of Kepler 22b, another planet. Here we get to Neptune. I mean, we're getting bigger and bigger. There's quite an obvious moment in this where you just think, wait, what? How are we that small? This is Uranus. Here we have Saturn, second largest planet in our solar system, and then coming up to Jupiter, our largest planet in the solar system. And then we have our sun. No, we don't. Oh, flippin' heck, it's like I haven't watched this already. Proxima Centauri, the closest star to us. And then we have the sun. There we go. Now, if I pause it there at the sun, you can kind of see how Jupiter and the sun, like, the sun isn't that much bigger than Jupiter. Jupiter, I mean, like, when I first did, I didn't quite clock just how similar in size they really were. Jupiter is nearly as big as another star. Because Jupiter is so large and because it has so much mass, the sun actually moves with Jupiter a little bit as well. Let's keep going there. We're only just under halfway, and there is so much more bigger things in the universe. Let's keep going. So after the sun, we get some bigger into Sirius A. Some before spoke about Sirius A and Sirius B. Here we have Vega. How many Earths can fit into the sun? That's such a good question. I don't actually know off the top of my head, but it's something we can look up. Here's another star. Now look, there's our sun down here. We have one of the smallest stars in the solar system. Sorry, in the universe. My mouth is not playing what my brain wants it to do today. It's one of the smallest stars in the universe, and we are nowhere near as big as we can really get to. Let's keep going. Here we have Rigel. I mean, you can just see how teeny tiny our star is getting, but then it just blows up into Betelgeuse, which someone spoke about before, the armpit of Orion, VY Canis Majoris. I mean, you can read it yourself at this point. I'm really hoping you're seeing just how teeny tiny we are. This is NGC 1277, which is actually another body in space. We have TON 6. I mean, it just keeps getting bigger, and there's a certain point. This is the Cat's Eye Nebula, one of my favourite. This is something that becomes stars in the first place. We've got the Helix Nebula. I mean, we're talking huge here. We are so small in this journey compared to what we're looking at now. Omega Centauri. I mean, I can't. I know we are so tiny, Leonardo. It is. I mean, one thing that this makes me feel, I mean, this is our Milky Way, just beautiful, but even our Milky Way, it just keeps getting bigger and bigger. I've sped it up as well. Anyway, we get to the observable universe, and I hope, just as an idea of the kind of scale that we're looking at so far, the kind of scale, we're talking huge celestial bodies in the entirety. We are so teeny tiny. We are so teeny tiny. We're so teeny tiny that it actually introduces a word that's one of my favourite words, because I think it's such a beautiful word. This word is my favourite word. It's something, there's a word that you might feel when you see that video, and you might feel something called insignificant. Right? This is not my favourite word. Not that I dislike it or anything. It's just, now, you may feel insignificant. Now, insignificant basically means that you have no significance whatsoever. That's not how I feel. When I see that, it doesn't make me feel insignificant. It makes me feel something called non-significant. I learnt about the term non-significance when I studied psychology at university. Non-significance is the idea that whilst it does something, whilst we have some significance, it's just not going to make the biggest changes to the universe. And this is the point, right? We are still making a change. You're all listening to me, you're all talking to each other, you're thinking with your brains, you're going to go away from this and tell other people that they are non-significant, and that feels kind of awesome, right? Because we're so small and non-significant that hopefully it just kind of relieves us of a lot of pressures of everyday life, and we can kind of just live and do the best we can and be nice to people and be compassionate, all these things, and just forgive ourselves, because ultimately, in the grand scale of the universe, which I hope you just saw, is humongous compared to us. Everything we do is just great as best as we can. We're not insignificant, we're not meaningless, but we're non-significant. The universe will continue after and has been going before us for billions of years. I think it's beautiful. And look at that. Anyway, I'm going to answer the question that we've kind of spoken about so far. When's the sun going to explode? Well, the life of our sun, the life cycle, or, when are we going to be engulfed in its ball of fiery death, it'll be something along these lines, right? Exactly, Leonardo. Even though we're tiny, we still have brains. So here is our star. It's been born, and this is it every billion of years. And here we are. It was born about 4.5 billion years ago. 4.5 billion years. That is a number of years ago, more than I can count in my entire lifetime. It would literally be impossible for me to count the number of billions of years it's been alive. If I were to count every second from now until my death, I would still not have counted to 4.5 billion years. But where the interesting aspect is where's it going to go from here? So at the moment it's in something called main sequence, which we're going to learn about later. Something called main sequence that we're going to learn about later, which is its main phase. The majority of stars are going through their main sequences. Over time, well, let's see what happens. We're going to get to our 6 billion years as it gradually gets warmer, than 7, then 8 billion years. But as you can see, it's starting to grow in size. There's a point where our sun will become something called a red giant. We'll learn about that later. It will then nova and become something called a white dwarf, and the end of its life is over here. It would start to darken to become a black dwarf. Now the red giant, the size of the red giant, it will get so big that it will actually engulf the first 3 planets definitely, and maybe Earth. But probably Earth, but maybe Earth. It's going to get so much bigger that all of our first 4 terrestrial planets are probably going to get screwed up. Now, if anyone remembers everyone's lovely way of remembering, or my, oh my gosh, so my very easy method just speeds up naming, and then it would say planets, but I just ignore that because Pluto's no longer a planet. But Mars, Venus, Earth, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Give or take our first 4, Mercury, Venus, Earth, and Mars, say goodbye when it's the red giant. Is our sun big enough to go supernova, shrimpanzee? Great question. I'll be answering it later. Let's have a look at this. This is one of my favourite diagrams that I've edited on the PowerPoint, one of my favourite programs. It's going to be opening up and showing us all of the sequences and life cycles of all stars over time. Now, all stars that you've ever known started in this area here, this molecular cloud, a cloud of dust and gases and beautiful things to make this beautiful set of colours that we like to call, does anyone know? I wonder if anyone can actually tell me what we call these areas. You know, we get this, and then slowly they clump together to form protostars, the opening. Yes, well done, Leonardo. We call them nebula. Nebula, or what I beautifully and lovingly like to call star nurseries. I can just imagine now a little nursery. Oh, I wonder if we should do that. All right, anyone here who wants to start a nursery, I feel like we should call it Nebula Nursery, because it's like we're you know, bringing together the bright stars that are the children that come to the nursery. It will go down so well. Look at this. This is an image, a collage of many different nebula, all collated throughout the universe. I'm sure you can agree that it's gorgeous. Absolutely, unequivocally gorgeous. All of these colours that you can see is this collection of the dust and the gases that are amongst the universe. The shape that they're in, that depends on what was this nebula before? Maybe the nebula before was actually a star in itself that went supernova and blew up in a specific way. Maybe it's just been a long time and they're slowly forming together. Sometimes we can have these incredible nebula which have this interesting shape like an 8. And you know, there's all sorts of ways that this can happen. And right now, we're going to have a bit of an activity of naming some of them. Now, these are my favourite nebula. Okay, these are my favourite nebula. Now, what I'm going to do is label them A, B, C, D, and E. And what I'd like you to do in the chat, please, is just type in what you would name these. If you were the astronomer who had found these nebula in the first place, you were the discoverer of these nebula, what would you name them? So what I'd like to do in the chat is type in A, B, C, D, or E, and be like, I would name it this. So D equals whatever, or C equals whatever. I will tell you their proper names, but right now, B, the jellyfish nebula. Love that. B, the jellyfish nebula. Thank you so much, Suzanne Tumnus. Shrimpanzee 12. C, the Eye nebula. C, the Eye nebula. Oh, E you meant. Understood. The Eye nebula. Excellent. D, the Quantum nebula. Love that. The Quantum nebula. I'm just going to write quantum. I think if I keep writing nebula every time, I'm going to go crazy. A. Oh, infinity. I love that. The Infinity Nebula. Gosh, because it looks like the infinity sign, doesn't it? The A is an hourglass. Ooh, that's a beautiful name for it. A, the tunnel. I love these names. These are really good. C, Grendel's claw. Who's Grendel? I have no idea who Grendel is. Should I know this? C is Skeksis. That is a cool name, Skeksis. I don't know if it means something, but I love it. C is a camel. Camel nebula. A, 8 eye. Oh, the 8 eye. I like this. 8I. B, the colour wobble. The cobble. C is the Wizard's Worlds. Love it. The Wizard's Worlds. What else we got? D is Wandering Lights. Wow, ominous. Man, there's a game I love playing called Dungeons and Dragons, and I'm going to definitely keep a lot of these words for it, because oh my gosh, they are so cool. Like, imagine, you know, I'm telling the party that are going along, and they go and find the colour wobble, colour wobble tower, or the Wizard's World's tower. What else we got? B is turtle. The Turtle Nebula. The monster in Beowulf. Oh, is that? Oh, Grendel is the monster in Beowulf. C, the Group of Death. I love that. It's a heavy metal band. The Group of Death. E is Turtle. Right, I'm going to go one more. C, the Claw Nebula. The Claw. Right, this is the actual names. Quite a lot of you have gotten pretty darn close, to be fair. I mean, someone wrote the Hourglass. I forget who wrote the Hourglass. It was Katana37. I mean, this is called the Hourglass Nebula. This is called the Crab Nebula. I'm interested as to why. Who wrote Turtle? Gosh, I can't remember. Penguins and Chalk wrote Turtle there. Yeah, they're very close. This is called the Pillars of Creation. The Pillars of Creation, one of my favourite ever, just because of the name of it as well. D, the Cat's Eye Nebula, and E, the Helix Nebula. Beautiful, beautiful nebula. Now, as I've said before, these nebula are the nebula which contain a number of gas, a number of dust, and what happens in them is that gas and that dust will clump together. They'll get closer to each other, and they'll clump, because each and everything in the entirety of the universe has a gravitational pull. So everything is going to clump together. A teeny tiny bit of dust is going to clump next to another piece of dust, which is going to clump, and then that piece of dust becomes like a ball, you know, the size of a basketball, and that basketball clumps to maybe another basketball, and that basketball is going to get bigger and bigger and bigger. And it reminds me of a video game that I absolutely adore, which I'm going to show you now. An absolutely beautiful video game called Katamari. Now, Katamari, I don't know if you've ever heard of before, but Katamari is an adorable little game where you are this little character, and the aim of Katamari is to roll around a ball, right? You just roll a ball around, and what you do by rolling this ball around is, oh, let's have a look. This is the launch trailer that I'm going to do just in. So what you do is, hold on, let's go for it. There you go. You roll this ball around, and the bigger it gets, the bigger are the things that you can attach to it. It's kind of really similar to that, right? You've got this ball of dust in the nebula, and they get bigger, so they have more gravitational pull, and because they're bigger, they can then attract even bigger things, and it just gets bigger and bigger and bigger. Eventually, with all this dust, all this gas that's in the nebula, they'll clump together and form the mass that will one day become a star, also known as a protostar. We then have this protostar. I see what you're saying, Leonardo, that it's a bit like a black hole in that it does have such a strong gravitational pull, but it's more that it's because it's not becoming it, it's all just joining together, and eventually will become big enough to become main sequence stars. And there's a number of types of main sequence stars. We've got the brown dwarf, which is one of the smallest, the low mass star, which is just like our sun, and the massive star, just like this over here. Something like Betelgeuse would be an example of a massive star. These stars are incredible. The way that they work, we're going to learn a little bit about now. So this is an image of the sun. Now, it's not that interesting, I would argue. This image here, it's a picture of our sun. Whoop-de-doo. It's actually our sun under what's known as visible light. Right, it's our sun under visible light. Now, what that means is that this is what we see if we've got a telescope and pointed it to the sun. Obviously, we shouldn't be looking directly at the sun, but we can get images through it on a computer. And there's not very much that we can learn about it. You know, if I really, really stare at it, there's not too much I can see. But that's why we're incredibly lucky to have different ways of imaging these stars. Now, Leonardo's asked what this little dot is. To be honest, I'm not sure. Now, can anyone think what this is? Now, this is still our sun. It's still our sun, but obviously we've got so much more information here. We've got these little spots here of something going on, or even these spots where it's a little bit brighter. Can anyone have an idea of what they think this is? Oh, it could be Suzanne Thomas. That'd be really cool. Maybe it is a planet going across. Now, in what way are we seeing the sun viewed from space? Brilliant idea, Leonardo, but no. If we did look at the sun in space, it would still look a bit like this because we're looking at it through visible light. But this is taking in the sun and viewing it with a different lens. We're not looking at its visible light. We're actually looking at something else. Anyone got an idea? Looking at gas clouds. Nice try. Okay, interesting. Anyone got an idea? I'll give you a clue. We can. This is actually looking specifically at the heat signatures of the sun. The heat signatures of the sun. Good. So what do we call that? If we're looking at something and we're looking at its heat and the way it heats up, what do we call that? When we're viewing something, we're looking at something through a specific lens, and we can start to see things as if, you know, if it was hotter, it would look brighter. If it was cooler, it would look darker. Thermal. Good. Can we think of another word of thermal? Good, we've got the idea. Infrared, GG Hall 35's got it. Fabulous work. But a thermal scope would work as well. Here we see the sun under infrared. Infrared is what ultimately heat is. If we're looking at, if you're feeling something warm, it's the thermal energy going into it. We can see that using infrared imagery. You can see that thermal imaging or infrared imagery is giving so much more information. Let's keep going. Here's another image of the sun. Oh, isn't it beautiful? Isn't it absolutely gorgeous? Now, can anyone think they can tell me what type of imaging are we looking at the sun through in this image here? We've had visible light, we've had infrared, and we've got this one here. Can anyone tell me what they think it is? Ultraviolet in one. GG Hall is on a roll. Yes, ultraviolet. And finally, the next one's actually my favourite. It is so beautiful. It is so beautiful. This one here, I just think it's gorgeous. Look at that. So this one here is ultraviolet. What would we call this one? Any idea? Another part of the electromagnetic spectrum. This one here in blue is the ultraviolet. What's this one going to be in green? This is something different. I could put money down that at least half the people here have had this radiation go through them. This type of electromagnetic radiation go through them. I could almost put money down. Actually, no, I know for a fact that we all have, but like specifically, yes, it is X-ray, right? So if we look at them, these are them under different telescopes. Okay, these are them doing different. It's just beautiful. You know, one thing can look so gorgeous in different ways, and because of this understanding of what it is, we can start to learn so much more about it. Okay, we can start to learn. Now, I'm going to go back to this image here, because I want to look a little bit about how the stars actually operate. Now, inside inside the core of a star is hydrogen. Lots and lots of hydrogen. Lots and lots of hydrogen. Now, hydrogen is the most abundant gas in the universe. There's more hydrogen in the universe than any other element in the entire universe. There's so much more hydrogen. And when, like we said before with the nebula, when all of these gases, and they mix up and they come into the middle, eventually, there's so much stuff, there's so much mass, there's so much hydrogen there, that hydrogen starts to fuse. What we get, exactly, incredible work, Leonardo, we get hydrogen fusing with hydrogen to make, as Leonardo's written, helium, right? And this process of hydrogens forming heliums, releases a tremendous amount of energy, and we call that energy fusion. We call this process, fusion. This is nuclear fusion. I've misspelled fusion. Fusion. Oy vey. This is where my spelling just becomes a little bit more dodgy. It is fusion. Lovely. It is an O. Flipping O. My brain is just having a great day today, isn't it? Right, this is fusion. It's in all of these. It's always happening. It's what's giving them all of this beautiful look, right? And this fusion Well, if there was the only one force acting outward, this amazing amount of force pushing away, then if that was always going on, then, well, the sun would explode, right? All of this force going outwards, that's it. But there's another force. And during the main sequence of stars, during its main time, during its main life cycle, this is what's happening. The inward force of something and the outward force of fusion, they are around about the same. That's why the star cell stays quite secure in its size. Anyone think they can tell me what this thing is? This other force pulling it all together, pushing it all together, increasing the pressure and heat in the center of the sun, in the center of the stars. As Fatima_Hass has said, it is gravity. Right? We have this pull of gravity pushing in, this push of fusion pushing out, and they are relatively balanced for the majority of the star's life cycle. So here we are, with our sun stable in its main sequence stage. This is where things get a little bit crazy. We get to the old age. This is where a sun, as we saw before, and stars start to break down, but because of that, they start to get bigger? Let's have a think. The smaller suns, smaller stars like our sun become red giants. Bigger stars like Betelgeuse become red supergiants. Huge red balls of energy and heat and light in the universe. Why? Why do they start to get bigger? Let's have a look at this. Now, here is a gorgeous image of a pre and post star becoming a red giant. Right, here's an image of a star that looks like it's been cut in half, and here's our red giant. Now, these aren't real images, these are just pictures that we're using just to work this out, right? So it's smaller, and something's happening leading to it getting bigger. Well, this is where a bit of physics comes in. I love this. It's so flipping cool. So in the middle, we knew before there was all this hydrogen, right? Hold on, I'll do it here. There's all this hydrogen, and it's becoming helium, right? It's becoming helium. And in that process, we've got gravity pushing in, right? We've got gravity pushing in. And then we've got, what color did I use for the fusion? It's alright, I'll just do a different color. We've got fusion pushing out. Now, there's actually a certain point where the hydrogen has fused into helium. The helium is then fusing, as Leonardo's just written, into bigger elements. But there's a certain point where that core, the inner, all of the elements in the middle of the star, it's not hot enough in there. There's not enough pressure in there for some of these heavier elements to fuse. So what do you think happens? What's happening less? We've got less stuff inside. Well, less things inside that are fusing. Therefore, there's less energy being pushed outwards. What do we think is going to happen to the star? Don't worry about this for now, but just with your own knowledge of these arrows. Amazing, Leonardo. It starts to implode. Katya Beer has written it starts to cool down. Therefore, these purple arrows exactly starts to collapse. These purple arrows get a lot smaller. What? Huh? So, hold on a second. If these purple arrows are getting smaller, then surely the star is going to get smaller because the force of gravity is going to collapse it. Well, that is what happens. But because that happens, because all of this mass is now in a more condensed space, the core and areas around the core start to get hotter than they were before. Now that they're hotter than they were before, more hydrogen is released from an outer area. Because if all the hydrogen was in the middle to begin with, there is still hydrogen around the outside, but it's not hot enough around the outside. But once it's small enough and gets even hotter, because so it gets colder, gets smaller, but then because it's smaller, it has got even more pressure, so it gets even hotter again. Then because it's hotter again, you've got hydrogen around it becoming available, then that starts to fuse again, releasing even more energy, and then the whole thing starts to get even bigger. And this is what happens over and over again. The star will use up all of the hydrogen, helium, and other elements that are fusing. It will use that up and they'll reduce. There'll be more gravity, so it will become smaller, but then because it's become smaller, it's even denser, even more pressured, so it actually heats up in the center, releasing more hydrogen. That hydrogen then starts to fuse again, and it grows even bigger again than it was to begin with, but then over time that's going to run out and it's going to get a bit smaller, but then even then it's going to get, and it keeps doing this, it keeps getting bigger and smaller, bigger, until it gets to this point of no return, and we get to star death. Things like red giants, they would become something called nova or supernova, eventually becoming like a nebula, as we've seen before. But red supergiants, these massive stars that we've spoken about before, those are the ones that have some of the largest supernova in existence and can eventually become neutron stars, black holes, white dwarfs, black dwarfs. We're going to look into that soon. But what is a supernova? What is going on? Why this explosion? All things must end. And our star is no different. Our sun is no different. Eventually will nova in one way or another, forming these. Now, we've never seen a supernova happen and form these beautiful nebula that you see here. We haven't seen it. This image here is just a GIF that is come from the internet that someone very, very talented has put together until quite recently. Because until quite recently, we got to see a supernova actually occurring in real time. This is beyond incredible. We see these nebula, these leftovers of blown up stars where all of the ions and the hydrogens and the heliums and all of these wonderful elements that have been created have been then expelled to the rest of the universe again, probably to one day again form another star. We haven't seen that happen until quite recently, and I'm going to invite you to watch this with me. This is a number of images that scientists have stitched together to create this occurrence. Now, this is the star that we're looking at today. This star here, I'm going to change my colour from purple. It's not as obvious if it is purple. Oh, not the highlighter. That could be quite cool though. I'm going to go for my pen, and I'm going to go for a nice yellow colour. So we're looking at this. Just check this star. This is a star, and just by chance, we saw it supernova. In less than a fraction of a second, it became this, right? Bam. This is so bright that all of the stars around it, billions of stars around it, were drowned out in this brightness. This is the real image of this happening. This is so bright. This is the brightest thing in the universe that human beings have ever observed in their human telescopic life. It blew up the heat of 1,000 million suns, and then started to recede and sort of go down again. And that's it. That's the closest we've had so far. I want to show you that again because it's just so cool. Right, so it starts like this. Bam. Huge light. And then it reduces in size. Gorgeous. And that's it. That's all we've seen. That's all we've really seen. It's so difficult to see, you know, to truly know when a sun or a star is going to actually nova. It's quite difficult to tell. I just think that's beautiful. Now, let's go back to our life cycle because we've got about 15 minutes left. So I want to go a little bit into some of the next steps. Once these stars have novaed, in the core, the leftover of this, Katana 37, how long did the whole process take? Such a good question. To be honest, I don't know off the top of my head. It's not something I looked up, but I'd love for you to find out if you can and tell us quickly, because I think that's really interesting. It was a question I actually had as right now. I was looking through it. If these, after we have these stars and they have novas, what's left over in the core of these novae are a number of different things depending on the size of the star to begin with. If it's a star like our beautiful sun, it will leave something called a white dwarf. A white dwarf is, basically speaking, the glowing, white hot remains of the core of that star done, right? It's just got leftover fusion. It's not getting bigger, not getting smaller. It's just slowly cooling down. It's beautiful, it's bright, but over time will become a black dwarf. A black dwarf of which we've never seen, ever, because they're so dark. We know that they understand. This supernova happened that we saw, I think it was within 10 to 15 years ago. If you type into a search engine, something like seeing supernova telescope, something like that, you should be able to find out more about it. Oh, thank you, Katia Beer. Maybe you've looked that up already. So yeah, it becomes a white dwarf it becomes a white dwarf, yes, if it's a low mass star. That will then start to cool down. That will start to cool down as a black dwarf, and that will just be this rock, used to be hot, now is very cool, floating around in space. If it's a bit bigger, massive stars, then we start to get into some of the really, really weird and freaky things that are going on in our universe. Something like a neutron star, which may become a pulsar one day, or the creme of the crop that we've heard about before, a black hole. Now let's look a little bit more into what these are as we finish off the Aim High today. Man, this has been so much fun. So, to be born again, we have here two images. This is Sirius A and Sirius B. Sirius A, which we looked at before, Sirius A is the brightest star in our night sky. Brightest star in our night sky. Quite a large star, quite a beautiful star. Only recently, relatively recently, because of just how bright Sirius A, we couldn't see it before, but we spotted this. Now, to many untrained eye, including my own, I would have thought, that's just another star, smaller one. It's a dual star. But no, Sirius B is in fact a white dwarf. This is the first white dwarf we ever saw. This is the leftovers of a star. It's still glowing because it's still hot, but it's on its way out. It's dead ultimately, and it is slowly cooling down to become a black dwarf. Over time it will become this. Now again, this is a CGI image. This is not something we've taken as an actual picture through a telescope. As far as my research went, I don't think we've ever seen one. But it makes sense, over time it cools down from this white hot star going down to be a black dwarf. Yes, Sirius B is a white dwarf. But now let's get on to some of the crazier things in the world. Here we have an image. Again, this is a CGI image of a neutron star that might eventually become something called a pulsar, right? Now, this neutron star becoming a pulsar, ultimately a neutron star is so horrendously massive, it is so horrendously dense, there's so much mass in one area that it has really interesting physics properties, a lot to do with electromagnetism, which is where it becomes a pulsar. This is really where my knowledge comes to its limit as a biology specialist. As a teacher, I just found this, and I'd love for anyone here to tell me or find out more and email it in to the Aim High team to tell me more about neutron stars and pulsars. But one thing I can ask you all that I'm really excited by, because this is some of the most bonkers information, is if I had, it's a classic physics question, a classic physics knowledge, right? If I had an Om-Nom teaspoon, and I had an Om-Nom teaspoon of the sun, right? If I had the mass of the sun, had an Om-Nom teaspoon of it, or if I had an omnom teaspoon of a neutron star. Question 1, what's going to be heavier? Question 2, can you tell me how much it would weigh in kilograms? Anyone got an idea? How much would a teaspoon of sun weigh in kilograms? And how much would a teaspoon of neutron star weigh in kilograms? I mean, it's a classic, the idea of getting it into a teaspoon. As if, I love the idea that there was just a scientist out there who just thought, you know what, let's make it real and let's just compare it with teaspoons. Do you think it was a British scientist, or do you think like an Indian scientist, or do you think, I'm thinking of different sort of tea-based societies. Japan has some incredible teas as well. Fatima_Has, my favourite dreams I've ever when 2 neutron stars colliding. Wow, that was a dream? Flipping heck. You think the sun would be heavier? Interesting. Must have been stirring their coffee all the time. What's heavier, our sun, a teaspoon of our sun, or a teaspoon of our neutron star? Penguins and Choc thinks the sun would be a bit heavier. Fatima_Has says that the neutron star would be denser. Interesting. Because time is of the essence, I will be giving some answers here. The neutron star would definitely be heavier. But how much heavier? A neutron star is incredibly dense, incredibly dense. There is so much matter, so much stuff packed into tiny, tiny spaces because the atoms themselves have become compact. If you could hold this teaspoon, how much would they weigh? Well, the sun, a teaspoon of sun is about 2 kilograms. 2 kilograms. 2 kilograms. Other things in the world that are 2 kilograms. Right? A newborn baby, give or take, is about 3.5 kilograms. Right? Ish, as I've just searched up online. Right? Between 2.5 is 4.5 is about normal, apparently. So a teaspoon of star is just a little bit lighter than newborn baby. I don't know if that helps with understanding. But the neutron star, how much do we think that would weigh? I'd love to hear your ideas. The worst you could do here is get it wrong. The best you could do is get it right. The most fun you could have is giving it a go. So I'd love to know what you've got to have to say for this. How much do you think a neutron star would weigh? Ah, a bag of sunflower seeds. Lovely. That sounds nice. Would you eat them, or would you plant them? Tons, yes. It would be in tons. 1 ton is 1,000 kilograms. I mean, it's many tons. 10,000 times heavier. 100 kilograms. Lots more. 2,000 kilograms. I am going to blow your brains off for feeding the birds. How lovely. Yeah, all of your brains. Okay, I highly suggest holding on to your skulls. We don't want to make a mess of the room around you, and I don't want to blow your head off from this fact, right? According to scientists, and that there are differences, it's around about, okay, anywhere between 1 to 6 billion, 1, 2, 3, 4, 5, 6, 7, 8, 9 kilograms. Between 1 to 6 billion kilograms. That's 1 to 6 million tons. Right? This is... How many babies? How many babies? How can I work this out? It'll be 1... Let's give an average of 3, 0, 0, 0, 0, 0, 0, 0, 0, 0, divided by 2. It'd be 100... What is it? 1,000 million... It'll be 1.5 billion babies. Wow, that's a lot of babies in a teaspoon. No, mate, that is bonkers. How heavy that is. Can you? The reason this has happened is because the atoms themselves, an average atom. You may recognize an atom as something like this, right? You may recognize an atom as something like this. We've got its nucleus, and around its nucleus we have our electrons, right? Here we have a classic nucleus of of helium. A classic nucleus of helium, where we've got 2 protons, these pluses, 2 neutrons where they have no charge at all, and 2 electrons flinging around it. Now the distance between here and here is huge. This is not to scale. To put things into perspective, if I had a sporting stadium, such as football sporting stadium, and I had something along the lines of a watermelon on the center line of a football stadium, the electrons would be all around the outside of the stands. I think even further than that. I'm trying to work it out in my head now. I don't have the exact facts next to me, but they're very far away. What a neutron star is they have squished those electrons so much closer, all of this empty space, they've squished it all so much closer together, meaning that other atoms which usually are, you know, at each other's edges, they are so much closer together now. You can just see how much denser those two are there compared to these here, if I were to draw them, right? So you can see around about the same size, but they can't get quite close enough, and the electrons won't. I mean, this is a little bit smaller, but I hope you get the idea, right? That if I've got it this much more small, I mean, this is incredible. With the last 6 minutes, we've actually ended just pretty much bang on time. I'm quite happy with this. I want to show you some of these. Obviously, this is the black hole, right? This is the black hole. Now, one of the worst things, in my opinion, I think that scientists has named this is called the idea of a hole, because it isn't a hole, right? As far as my research has gone, this isn't a hole. It's not like ripping through a hole. It's not a empty. It is a thing, you know, this is a celestial body in the universe. This celestial body they called a hole, as far as I'm understanding, because of just how dark it is. The idea behind it is that it has so much mass, it is so dense, its gravitational pull is just so astronomically high. And this is one of the few times I can say astronomically high in a very accurate sense. We are literally talking about the astronomical plane. Astronomy, massive, it's so high, this gravitational pull, that light itself, which travels at 300 million meters per second, right? This incredible speed. Light itself gets bent round it, and if it isn't able to escape by bending round, it actually gets sucked in. And because it gets sucked in, it doesn't escape. Therefore, it just has this blackness, because the light coming in does not come out. It stays within, so it looks really dark. It looks really dark. It's literally the darkest thing in the universe, because light doesn't bounce off it. Light only goes in. However, recently, I'm sure many people listening have seen this image. It is legitimately one of the most incredible images that can be taken. Is this seemingly nonchalant, little bit blurry. This is the closest thing we've ever come to an actual image of a black hole. And remember, because this image was taken using things like light to indicate what it is and other forms of electromagnetic radiation, it's not very clear, and we can't really see it, because remember, electromagnetic waves, like light, they get pulled in, so what we can see is what light has done around it. And this is our first image. The amount of time, effort, and incredible learning that went into finding this out is just incredible. Now, what I want to finish off is going back to this. This image that we built up today, I just think is absolutely beautiful, and something that I hope you want to maybe take away with you if you so wish, or something like that. But I just think it's gorgeous. If you want to take like a screenshot or something, you can. This is just so cool. Here is our main life cycle of all stars. Now, thank you so much for coming. It has been such a pleasure to have you here. We really hope you've enjoyed the lesson. We'll be back at the same time next week with another learning objective, another learning adventure. The next learning adventures coming up are going to be absolutely incredible. I hope we're quite excited for it. What's coming up next Tuesday is How Many People is Too Many People by teachers Matthew Shribman and Paul Turner at 7 o'clock UK time. You can sign up for this and check out more lessons on our calendar by heading here. I'm just going to post it to you all. Here you go. There we go. Oh, there we go. There you go. There's our calendar. Please tell your friends and family about our Nature First, curiosity-powered online school and our mission to make the world-class live learning accessible for all. Okay. If you want to join our Discord, there's some really cool stuff going on there, which I've just posted. And there's a bit of a challenge. Okay, I'm actually going to type it in as a full. If you'd like a chance to win £100, you can get along with our latest challenge. It's called the Future Dictionary Challenge, and the head of the Oxford English Dictionary is one of the judges. The aim is to invent an entirely new word, something that's going to be used in the future. Part of our progression as a human race is about creating new terminologies, talking to each other in communication. If you can think of a new word, what it means, that would be incredible. Thanks to some generous support, there's quite a lot of them, the prizes are £100. Please spread the word, especially to schools and universities if you'd like to. Oh, the Discord link is invalid, then I'm not sure where to get that. To be honest, I'm sorry. Maybe we can get, it'll be somewhere on the website that I can get to. If you are a student and you're under the age of 25 and you want to be actively involved with Aim High, what you can do if you want is to become an ambassador, which I've just posted, to make it nature first in education, make excellent live lessons accessible to everyone. You want to join in. And if you don't already know about the work to spread brilliant, accessible, empowering and uplifting climate and nature education, check out this link, because you might want to join in on our climate course that we've got going on. Our work is supported by Cambridge, the Eden Project, promoted by the UN. It's recommended for anyone 16 to adult, but please come at any age. It's ideal if you're looking to fully understand the global crisis of climate change and how things are impacting the world, how to make an impact yourself, or how to even be a leader of positive change. The second to last thing is that if you're at all interested in the Aim High tutoring, every Monday me and other tutors teach different aspects of the world. At the moment, next Monday, I'm going to be looking at the neuroscience of fish. I just remembered. Oh, we're going to look at the neuroscience. When is it? On the 19th of April. Yeah, we're looking at neuroscience and marine biology. That is going to be so flipping cool. I'm quite excited for that. I'm not entirely sure what it's going to be about. I need to do a bunch of research. It's going to be so cool. Fish and their brains. Anyway, if you want to, please follow all of our socials. They're all around me right now for updates and memes and mailing lists and all other really cool things. You've been incredible today. Have an amazing rest of your day. If you're on Easter break, have a brilliant Easter break. Much love to all. Have a great day. See you later on. Yalla bye.